Hello and welcome to our webinar, The Guide to Successful AI Projects. It's a couple of minutes left until we will start, so just hang on and we will be back with you shortly. Hello and welcome to our webinar, The Guide to Successful AI Projects. It's almost 3 o'clock Central European Time, and we are going to start in just a couple of minutes. There's quite a lot of people joining the webinar right now, so we will wait another 2 or 3 minutes before we start. So just hang on. Hello and welcome to our webinar, The Guide to Successful AI Projects. It's now 2 minutes past 3 and it's time for us to start. Before I hand over to today's speakers, I just want to inform you that you can use the question mark icon on the GoToWebinar control panel to ask questions. You can type in your questions whenever you want, and we will answer them in the end of the webinar. Other people that participate will not be able to see your questions. We are the only ones who will see the questions. So I would like to hand over to today's speakers from Imagimob that's hosting this webinar today, Oskar Sverud and Johan Malm. The stage is all yours. Take over.
Thank you very much. So, welcome everybody. Okay, here we are. My name is Johan Malm, and I'm a researcher at Imagimob, where I'm developing AI algorithms running on small microprocessors. I've always been interested in nature and physics, and I have a master in engineering physics from Uppsala University and a PhD in flow physics from KTH. In the last 12 years, I've been working with scientific computations, first in my own research in fluid dynamics and turbulence physics, and then later on when I developed weather forecasting models and inertial navigation systems. Some years ago, I started to read about AI and the intelligence explosion, and I was overwhelmed by the potential I saw in this area. So now here at Imagimob, I'm very glad to have the opportunity to work deeply with AI, and currently I work on feature extraction for time-dependent problems.
Thanks, Johan. My name is Oskar Svirud. Hello, everybody. I am the COO at Imagimob, and my role at Imagimob is to make sure that both projects and product operations are efficient. Ever since doing research in computational biology using AI in the early millennia, AI and machine learning have been one of my main interests. And now with the upswing of AI popularity, I have the privilege to combine my career creating efficient development teams and the exciting progress in using AI to solve real-world problems. And at Imagimob, we get the chance to work with leading global companies using AI to solve these or help solving these problems.
Okay, so this webinar is about AI. And before diving right into it, we need to define what we mean by AI. And to do that, we need to first define intelligence. So the intelligence is about the ability to acquire and apply knowledge and skills, which means that AI is the artificial way of acquiring and applying knowledge and skills. And it was in the 50s that researchers in computer science first started to realize that this was even possible. But to make it possible, computers need to be able to do three fundamental things, which is to store data and to compute data based on this stored data, and to learn and adapt based on new experience, that is new data that's coming in. And these 3 points are basically the building blocks also for our own mind and intelligence. Computers have for a long time been very good at the first 2 points, but now recent advances in computer science have also made the last point possible. I should just briefly mention that we can divide AI into artificial narrow intelligence and artificial general intelligence. Artificial narrow intelligence refers to a machine that is very good at one specific task and can learn from experience to get even better. Examples are spam filters, movie recommendation, weather forecasting, natural language processing. In other words, all of the AI that we have today. But in the future, we might have the possibility to also build artificial general intelligence, which would then have general intelligence like our own. And this may sound like science fiction, but it's actually very well possible. And many AI researchers think that we are able to reach this level in about 30 years from now. Sometimes you also hear the term machine learning, and we also used it during this webinar. So I just want to explain this briefly. Its relation to AI is easily shown by this figure. So artificial intelligence refers quite general to a machine that can sense, adapt, and act autonomously. Machine learning is the area of computer science and statistics where algorithms are designed to learn from data. And here we have various classes and types such as tree-based algorithms and the ones inspired by the way our own brain works, such as neural networks and so on.
Okay. So before we show the agenda today, we will first shortly talk about disruptive technologies and the definition. So it's all about the factor of 10. So it's a times 10 improvement of product performance. It happens fast, often within 10 years. And of course, disruptive technologies normally have the effect that well-established companies goes bankrupt due to the fact that large companies normally work with incremental improvements. And one very famous disruptive technology is the car. So this is a picture taken in New York in 1903. And in the picture, you can only see horse-driven carriages. And 10 years later, 1913, at the same spot, it's only cars. So this happened within 10 years.
Or maybe one horse.
Maybe one horse in the picture, yes. And there are, of course, modern day examples of this. We have mechanical calculators disrupted by electronic calculators, and we have video rental companies disrupted by video streaming services. We have analog cameras was disrupted by digital cameras, and then we have feature phones, which was disrupted by smartphones. And then, of course, the question is AI disruptive technology? And for example, the automotive industry is rapidly changing by companies using AI technologies. We have the healthcare industry, and they have seen major changes the last years, where doctors may not be replaced, but their daily work will dramatically change. And then we have traditional marketing that have been disrupted by AI-based targeted marketing. And then, of course, we have other sectors such as finance, education, and production, which is also about to get disrupted by AI. And this slide is very interesting and important. There's a quite bold statement here. So I'll read it right off the slide. So AI has the potential to virtually disrupt any industry on the planet that stores and handles data. And more or less, this means in the long term that AI has the potential to disrupt any business, since almost all businesses today handles data. So we get to the agenda today. So what's the agenda again?
Yeah, we will see a little bit more here why we would use AI and what for. Why is it a good approach?
Okay, and then we have what we need to think about when starting an AI project and the project process. And this is the main topic for today. And we will go through that in a step-by-step manner. And for each of these steps, we will give some background, we will discuss what questions to ask yourself, and give some lessons learned.
Yeah, and if you have decided to look further into AI, how do you start? So here we will talk about some hands-on steps for you to take. And throughout the webinar, we will be discussing the importance of data in various aspects.
Yeah, and also as Lars mentioned in the introduction, remember to post questions during the webinar. So over to you, Johan. Let us know a bit why we should use AI.
Yeah, it's quite, or I think it's very interesting and fascinating because we're now facing an ongoing revolution. So we discussed that AI may be disruptive in some sense, but why is this? So to qualify being useful, it must solve a real problem. And it's actually quite easy to understand the power of AI. Compare the efficiency in digging in these two pictures. It's quite obvious that the machine is solving a real problem and make the process more efficient. And the thing with AI is that it opens the possibility for machines to do much more advanced work than has ever been possible before. So this efficiency revolution, you could say, is entering new fields. And this is an example of something that is being put in production right now. Machine learning algorithms are now capable of diagnosing cancer at the same level as humans, or even more accurate, actually. And this is mainly due to two things: advancements in the field of machine learning, AI, and other related fields. And the other is due to the fact that we have so much more data available in the world today than just a few years ago. So this shows that machines are really doing work that has been regarded so advanced that only medical doctors with a very long education were able to do this work.
Okay, assuming that many of you who are listening haven't embarked on the AI journey yet, in our experience, there are a number of challenges to be solved even before starting a project. And the first one is probably that there is no or little understanding in the organization about the benefits that AI can bring. People usually know it's a new and fancy technology, but what are the real benefits and what type of problems can it be applied? And of course, internal education on AI needs to be done. And this is part of the competence. So the second one is competence. Where and how do we find people that can do this? And this is tricky, and most organizations don't have the competence in-house. And even if there are companies out there specializing in AI, you can get help from. It is very important that you as a customer have the right knowledge and the basic understanding of AI.
Yeah, that's right. And assume now that you have done a great job of convincing the management about the benefits. So how do you start? There is some new thinking to get accustomed to. The first is data, and the commonly used phrase today, maybe a bit worn out, but anyway, data is the new gold. Data is the fuel for all the results, and this is kind of a new thinking if you are used to governing equations and things like that. Data needs to be stored before you can get anywhere. The second is that the logic is set by the algorithm now and not by your pre-programmed rules. All right, so before starting, the main class of machine learning model needs to be chosen. And the three main categories are supervised learning. Here we have labeled the data in such a way that the algorithm knows what is the correct answer. And the task is typically to do some classification or regression. Examples can be spam filters, speech recognition, biometric analysis. Then we have unsupervised learning, which is the computer doesn't know the correct answer, but it can see patterns in the data that is not visible to humans. And so here usually the computer is performing what we say clustering or association task. For instance, people that do X, they also tend to do Y. And then the third class is reinforcement learning, where trial and error is the keyword. So the computer program learns what is right and wrong based on some reward function. Here we are going to get deeper into supervised learning, and Oskar will talk about the overview of the process here.
Okay, so this is the overview of the AI project process we will cover today. And at Imagimob, we have been running over 20 AI projects the last years. And from this experience, we have created an AI project process that can be applied. And we have identified 10 steps, and they can be divided into 3 phases. And the green marking here in the process is the first phase, and it's all about the data collection. Then we have the second phase, which is about the AI implementation and training. And then we have the third phase, which is about applying the AI on the target and deploying the solution in the real world. And each of these phases are divided into steps. So we will cover these steps in detail in the coming slides. But before we go into these steps, we will describe the use case that we will use today. So Johan.
Yeah, so this is a case that we will show this in conjunction with these steps so that you get a better feeling and grasp what we're doing. And the case we've chosen is a project we have done together with the company Bellpal, which was founded in 2016 by David Siemski. And his mission was, or is, to make our parents be able to age comfortably and with freedom in their own homes. His idea is to equip nice-looking watches like these with the fall detection alarm system and positioning system. And why would you even need an AI approach for this? Well, David made a thorough study of the market and found that there are no so good ways to detect falls in the old traditional signal processing way. And the reason is that you can fall in so many different ways. And this is normally how it goes. If you find your problem difficult because of the complex nature of it, or the many combinations of the input data, or if you have to recognize complex patterns, then AI is the way to go. But in many cases like this, this requires what we call edge AI. So Oscar, what is the challenge using AI in the cloud?
So yeah, the AI in the cloud. Yeah, normally AI applications are quite resource hungry, which means they're normally run in the cloud. But of course, this poses some challenges. Devices need a continuous internet connection to stream the raw data. Sending data from the device to AI processing in the cloud and then back to the device means, of course, large latency. And then, of course, since we transmit all this raw data, we get a high power consumption because we need some kind of, for example, wireless connection. And of course, there are data privacy concerns when you need to stream the raw data to the cloud. But I guess, Johan, there's a solution for this, right?
Yes, fortunately, there is a solution, and it's called Edge AI, which moves the AI processing from the cloud to the device itself. And what we get is low latency. We get real-time processing and low power consumption because we will not stream the data all the time, but only when something interesting happens. So think of all small devices out there that suddenly become autonomous, with the decision process being local. I think this is quite fascinating in my mind.
Yeah, I absolutely agree. And for doing this, Imagimob have developed a few software packages. And in relation to the 3 project phases we mentioned earlier, we use 3 software packages adopted to these 3 phases. And the first one is the SensorBeat capture software, and this software is used for collecting data from various sources.
The second is the SensorBeat analyzer, where we can label data and train the AI model offline on a PC.
Yeah, and then of course there's a third software package, and that is the SensorBeat library. And that's the software library that is deployed on the target hardware together with the trained patterns for real-time execution.
Yeah, so now we will go into the process more detailed. So I just want to remind you to post all your questions at any point. We'll answer them at the end of the webinar.
Okay, great. So what about the first slide?
Yeah, this may seem obvious, but actually you should get dirty and get to know the application. You should ask yourself if the problem can be solved using a traditional approach, because AI shouldn't be applied to too easy problems, actually. A good rule of thumb is that if the problem can be well described by equations and rules, then you shouldn't use AI at all.
Yeah, and then of course there's a few questions to answer. And first one is accuracy, and accuracy means normally two things, and that is the rate of true positives, more or less how often do an event get misclassified, and the other one is false positives. At what rate do we accept a classification when there should be no classification at all? And it's really important to investigate what this means in relation to the end user of the product. And in the Bellpal project, the trade-off boils down to how often it is okay that the AI does not detect a fall compared to how many false alarms would be acceptable for a user. And then we have performance and latency. And performance and latency and real-time behavior come hand in hand. So the questions you need to ask yourself is how fast do we need a response from the AI system? And normally there's a trade-off between the accuracy and performance. And this, of course, differs greatly between different projects. And then we have the model update question. So this is about updating the AI models. It can be quite tricky. So can we expect initial training data versus real data getting biased over time? Or in other words, does the application require that the model is retrained or continuously getting updated on new data? And then, of course, hardware. And it is essential to understand what type of hardware will be available very early on in the project, since it can affect design decisions. So what are the limitations on processing power? Do we have limited memory, and do we have power consumption constraints? So, Johan, over to you. Are there any lessons learned on this?
Yeah, I would say something you tend to hear is that the accuracy should be very good. And yeah, of course, customer wants it to be good, but what does it really mean? It's important to define this limit together with the customer. And then I should say, choose hardware and sensors in harmony. And by that I mean that the CPU and the sensor shall have roughly the same quality and draw a similar amount of power. Because if you have a sensor that has a very low power consumption, but on the other hand, high noise values, then the CPU has to filter harder, etc. And it's not.
Yeah, and I guess one lesson to learn here, at least from the Bellpal project, was that battery power consumption for watches are very important. You don't want to charge them every day.
No, exactly. That's the main thing here to make the battery life long.
Yeah. Okay. So now we get to step 2 on the AI project process. And this may seem obvious, but our experience is that it can be a lot of work to collect good data. And this is not something you want to do over and over again. And therefore, it is very wise to work through a data collection strategy and, of course, test strategy. It is important to early in the project know how the system can be tested. So over to the questions. What is important?
First I just want to point out that the data collection process might look very different depending on your business. For us, the main ingredient has many of our projects been motion data in different forms, typically acceleration data and gyro data. And on the picture here, you see one instance where we collect this motion data. But it could also be like customer behavior or things like that. So it's your imagination basically that sets this limit. But the time spent on ensuring the quality of the data usually pays off. The main reason is that the quality of your model will not be better than the quality of the data, since your AI model is built on data. And yeah, it's quite simple, but it can be easy to foresee in the beginning when you start to collect your data. And there are several aspects to check for here. One is diversity, and another is bias in the data. And I could, here's an example that you could quite easily build in a bias to your data if you're not careful. So the example is this. If you want to train a model to judge whether a visitor on your web page is going to sign up as a customer or not, you need to feed data that contains all kinds of visitors, not only the ones that finally became a customer. So this may sound obvious, but it's not actually always obvious in our experience. Yeah, the other one is how much data do we need? And this is a question that usually comes up, and it should be because it's important, especially in the planning stage. The boring answer is that it depends. It depends on the complexity of the problem. Because think of this, on a high level, you're trying to find the underlying function that relates your input to your output. And the more complex this function is, the more data you need. It also depends on the model you're using, where some are more data hungry than others.
Okay. But you say it depends a lot, but aren't there any rules of thumbs to use?
Yeah, you can find some. So to help guiding you, you could use a few rules. There should be at least 10 to 100 data points per feature dimension to avoid overfitting, which I will go into later. But what I mean is that we need 10 to 100 examples per input category, so to speak. And this usually means that no fewer than hundreds, but preferably thousands or even millions of individual data points are needed. Another rule of thumb is, if you're dealing with neural networks, is that the number of training examples should be at least 10 times the number of weights in your model. But what you practically can do is to monitor the so-called learning curve, which essentially plots the performance of the model versus the size of training set used. But try to get hold of as much data you can, because it's easy to skip in the end, but it's very time-consuming to generate more.
Okay, so for the lessons learned for this at Bellpal project, the specific problem was, of course, to get people to fall naturally. And the main reason is that falling includes hurting yourself. And as a funny example, or not very funny, but the Bellpal founder, David Siemski, he actually he got a fracture in one of his ribs during one of the data collection sessions. And another problem for Bellpal was that the recordings were used or was done on soft mattresses. And that is, of course, not the normal way people fall in real life.
And how did you solve this?
Yeah, so what we did was we mixed the data from recordings of humans with human-sized doll. But that of course posed other problems since they were not humans. But what we can say about the Bellpal project was that the data collection have been quite a challenge.
Yeah. Okay, so finally we got into the step where we are about to collect data. And as we said, this is a process that might have to start much earlier than you're able to start with your AI project. So Oscar, how do we do this?
Yeah, so for us, it's usually about putting accelerometers or gyros on people or other sensors, or on people, machines, or other gadgets, and then record the data. And this, of course, is normally done according to the data collection strategy that was built in step 2.
Yeah, and as we say here on the slide, the test data should be separated from the training data. Because the training data is the data used to train a model in supervised AI. The test data is the data used to test the final accuracy of your model. And validation data is sometimes, but not always, used to tune the model. And it could also tell you when to stop training. All these data sets are randomly picked from your original clean, ordered, and labeled data. The randomness here is super important if we want to get a good model and a proper answer about its performance. So the ratio that you split this data in can differ, but typically in the order of 50% training data and 25.
And I guess that the 50% is training.
Yeah, it's the bulk of the data is used for training.
Okay. And the beautiful thing that is normally that we don't need to collect the data on the target hardware. It is enough that we can record the data using similar sensors or a hardware setup as in the final product. And in most cases, we actually don't have the final hardware at the data collection stage. But what we normally do is to record the data along with time synchronized video. And this is in order to make the data analysis and labeling easier. So I guess we have learned something from this, right?
Yeah, what you normally realize is that it makes sense to collect data iteratively and analyze it early to see that it looks reasonable before you do the bulk of the data collection. Is your data capturing what you want to capture? In the Bellpal project, it was also crucial to collect data from normal user behavior, and especially from situations where data could potentially be confused to the full scenario.
Yeah, it's about the true or false positives.
Yeah, exactly. Yeah.
Okay, so step 4. So this is the step in the AI process to make a sanity check that all the data collected and to do the labeling of the correct classifications. And as mentioned before, it helps having a video with synchronized data. And the reason for this is that it's very difficult for humans to navigate when only seeing raw sensor signals. But I guess also a question is, can we in some way see that the data collected is good data?
Yeah, here we get back to what we said before about statistical properties of the data. So by using different statistical tools, we can check that we have the expected distribution of our data, for instance. And to see that we don't have a bias and the data should have enough spread and so on. Right.
Okay, but yeah. But I guess one of the things we have learned is that data is never clean, so it needs to be clean, because sometimes during recordings you forget to shut down the capturing or stop and start at the right times and so on. And learning the model, the wrong labels can be quite time-consuming, since it's a bit like finding tricky bugs. And also it's very important to be consistent when you label data, especially when you're dealing with time series signals. And of course, since human memory is short, it is very good to do the labeling as quick as possible after the collection was done. so you remember what you did, kind of.
Yeah.
So now I guess we're at architecting the AI model. So now it's getting interesting or exciting.
Yeah, this is that's right. At this point, we know the task thoroughly, and we know the data. So it's time to architect the model, and it usually involves a series of steps from feature engineering, where we treat the raw data and create some features out of it. We call it. And then dimensionality reduction. So we get rid of quite many of these features because they are not telling us important stuff. And then we combine a set of machine learning models to do the pattern recognition and classification. For embedded systems that we work with, the feature engineering and dimensionality reduction are very important to reduce the amount of data.
Yeah, I guess that's because we don't have much processing power.
No, we have very little processing power and very little memory available. So memory constraints, processing power versus performance and accuracy are normally trade-offs. Since we aim to run AI on the smallest MCUs on the market, we have to design our own AI models. So those you won't find in any textbook. Yet, at least. Any lessons learned at this step?
Yeah, I guess one of the lessons learned here is that it's vital to involve the AI expertise early on, and even, of course, even before you've actually set the hardware.
Yeah.
And that's true, of course, for MCUs, but also the type of sensors and so on.
Yeah.
So you get this balance we talked about earlier. And if the last step was exciting, now we're at the really exciting step where we can start seeing if the model produces any results. And I guess this step can feel a bit magical when the system for the first time takes decisions by itself, right?
Yeah, it's like seeing your newborn baby learn to crawl. And even though you know that the model is just finding decision boundaries, like down on the technical level of it, it surely feels magical. And in some way, it is, because the computer sees stuff that we don't see. And also, if you think about it, our mind is also a collection of very simple signals that together creates this rich and complex network. But okay, so when you train the model, there are a few things to look for. One important one is overfitting, as I just mentioned before. This means that your model has been trained too long, and therefore we have started to learn not only about the underlying trend in the data, but also about its noise and inaccuracies. So our model becomes too complicated and can therefore not generalize anymore. In other words, giving the model some test data would produce a quite bad result, whereas the result on the training data itself is excellent. So here's an example. Think of a line that tries to capture some overall trend in some data set. If you draw the line from point to point in the data, it will obviously not teach you anything about the trend in the data. But there are a few tricks that you can use to avoid overfitting. Basically, we want to stop training before the model overfits. And so we want to monitor how well it generalizes in every time step. We can't use either the training data for this or the test data, because that one is saved for the end test. So here we need another data set, which is the validation data. And here I show you a technique called early stopping. So what you do is to plot the error in your model as a function of each given set of trained weights. And we want to find the minimum of the error in the validation data, which is the red line here. where the model has trained long enough to learn about the underlying function, but not about the noise in the training data. The training data is the blue line here.
But I guess one question you would ask is, can we always reach the accuracy stated in step 1?
Well, that depends. Maybe you need to test another model, or maybe you need to work on your features so that they become more discriminative, which means that they are representative for the various phenomena you would like to capture and classify. And this is, in our experience, where you normally spend a lot of time. At the same time, if you do a good job here, then the pattern recognition and classification becomes an easier problem. Maybe you need to collect more data too.
Yeah, and to the lessons learned, in many projects, a powerful way to lower the false positive rate is to train the system to classify non-events. And in the Bellpal project, this would mean to actually include non-false in the training set. And this can be done either by figuring out these cases beforehand, or to record which normal activities render a high frequency of false positives during testing, and then add those cases to the training set with another classification label.
Yeah, so
this is like the 3 last steps.
Yeah, exactly, in one go. We end the process by test the AI model using the test data set. If the performance is not good enough, you go back to step 7. But once you're happy with the performance on the test data, it's time to deploy the system in the real world. And what you normally do is to do the testing with the test data on a PC or a cluster, and then as a prototype on the real system in an online situation, or on target, as in our case. This will then test the real-time aspects and other memory and timing issues of the model and the system as a whole.
Okay, so for this step, the questions to answer is, of course, do we reach the accuracy? Do we reach the latency demands? Do we reach the power consumption? And of course, then what does the end user say? And testing the prototype or product in a small scale is usually the way to go here. And then, of course, we have what are the consequences for outliers or misclassifications. And testing for scenarios not being in the trend of the training data set is much part of the testing, of course. So
yeah, for
lessons learned here.
Yeah, for this case, I think it was the doll that made a difference, because we really had to have training data made on hard floors, because that's how it usually goes.
Yeah, and I guess we actually also used that from the last slide, that we added classifications that were commonly misclassified as false, right?
Yeah, exactly.
Yeah.
All right, then we.
Okay, so to the summary. So today we have discussed that AI is potentially a disruptive technology, and this is for many businesses and industries, if not all. We have looked at some examples of AI applications today, and we have given a brief introduction on how we at Imagimob look at the AI project process based on our experience running AI projects. So before we go into questions, and there's still time to file the questions if you have any. We still have one thing left to share to you all.
Yeah, and here I think it's very important to get the common strategy for AI in the organization, and this is from our own experience. We have been working at large companies, and this is really the first step. So I would say call for a meeting with some developers, experts, and management, because if everybody has a basic knowledge about the possibilities and a rough idea how AI works, then there's a higher probability that you'll together find an unexplored spot in your organization that could be made more efficient by using AI. And as we said, the problem should be complex enough. So the statement in this picture may have been a bit exaggerated, even for my favorite physicist, the brilliant Mr. Feynman. But even if it's not extremely complex, there are still benefits using AI, since, for instance, software maintenance can be much simplified. And I would say also start to look for parts in your organization with high cost or low margins, where there are repetitive tasks that humans are notoriously bad at. Ask yourself if you're spending a lot of time trying to solve these problems. It can be a good indicator that you're not working as optimal as you could. Look at your organization with I call it the optimization glasses on. Maybe you can make something 50% more efficient by hiring a really good employee, or maybe 100 times more efficient by using AI. And lastly, the last point here is collect some data. We've been discussing the importance of data throughout the webinar, but since data is everything really to get an AI model to learn, you must have a strategy for data collection. Maybe you generate a lot of data, but you're not storing it. Start to collect some of this data. It's better to start now than to wait, since the time to collect good data can in some cases be considerable. But even if you start simple, don't forget to capture the important parts of your problem, as we've discussed. And as an example, maybe you could skip some data in time, but don't throw away certain events or cases so that you risk ending up in a biased situation.
Okay, so if you need further advice and tips to start an AI project, don't hesitate to contact us. And what we typically do is to book a short meeting at our facilities in Stockholm, or that we come to you. And depending on the art of the use case, sometimes we even run a short workshop together with the customer before actually writing a project proposal. So now it's question time.
So thank you, Johan and Oskar. We're moving over to questions and answers.
Thank you very much.
There is some questions, so we'll see if we get some answers.
Okay.
All right. Yeah, we have a couple of different questions that has been sent in, and the first question is relatively straightforward. Yeah, I guess it's most efficient if you stand sort of beside me here. What are different sensors? What type of different sensors can be used with your products in real time? So, what type of sensors can be used with the edge?
Well, yeah. In our case, it has mostly been motion intelligence. So it means some kind of sensor that detects motion, and usually that is accelerometer or gyros, but it's not limited to that.
I think we can say that the majority of projects are using time series sensors, so not usually images.
No, right,
but
many different types of sensors. Doesn't have to be any specific
but we have a lot of experience with different sensors, especially with accelerometers and gyros. So we actually know which ones are good to pick for low cost applications.
Yeah, so you can help out from that aspect as well. What type of sensors to use? All right. Then we have another question here. what are the best ways to handle false positives and false negatives? Do we understand the question?
Yes.
Who wants to answer it?
Yeah, Oscar, you talked about it during the presentation.
Yeah, for false positives, as we mentioned in the webinar, one very good way is to actually include these events in the training data and classify them and like force the model to see the differences. More or less, in technical terms, it's about creating decision boundaries that are quite tight. And of course, for these cases, if you make the decision boundaries very tight, you kind of lose some of the possibilities to add variations in the model. But this is a trade-off you will have to make in order, depending on the project, which is most important in this regard.
Yeah.
Okay, another interesting question is, what tools have you used for this example for Bellpal? And I guess tools in this case is, except for the dolls, is the different type of software components and sensors that you're involved in.
Maybe that's what meant by tools.
I think so.
Yeah. So we've used the tools that we have developed that we usually use, which is these 3 tools that we showed, which is the capture tool, capture device, where we record data, and then the analyzer software that we use on a PC to train the model, or the library that is then executed on the real embedded system.
Okay, we have another question here. Thanks, was very helpful. Will you share the slides? And yes, so everybody knows, you will receive an email after the webinar, most likely tomorrow morning, with more information on how to get in contact with Imagimob, and also a PDF version of the slides.
And I would also like to point out that parts of this webinar is based on a white paper that is downloadable on our webpage.
Exactly. You can go to the web page and find it there under white papers. Yeah, okay. All right, let's see. We have some more questions. What are the best hardware available today for deployment?
Yeah, so as we said in the webinar, we're actually focusing on being able to run on the smallest MCU. So this means that we can run our AI system on ARM M0 MCUs from different vendors and different operating systems. But in practice, since the product usually runs other firmware than just the AI system, normally we use M3 type of ARM M3 type of hardware. And for example, this watch, which is the use case, is running on M3.
Okay. Yeah, we're almost running out of time here, but I think we will be able to cover at least one more question. If we're not able to cover all your questions, and I don't think we will, we have sort of recorded your questions, and we can come back and answer the questions via email to you after the webinar. So another question. Regarding fall detection, could you comment on what model you ended up with? CNN. How many layers did you end up with? Did you use raw accelerometer data, or did you have transform it in any way?
Interesting question. As I mentioned during the webinar, our model is not something you can find in a textbook. It's a combination of our ideas and yeah, it's innovation that we have. So it's really targeted towards running on small MCUs. So it's
But I guess we can disclose as much as it's not CNN and it's not a typical neural network architecture.
No, that would be too memory hungry.
Yeah. And also, of course, there's some dimensionality reduction and feature engineering involved in this.
Yeah, exactly. As here in the question, do you use a transform in any way? That's usually very efficient to start off doing a transform in some way to see the data in a different way. That's usually very, very efficient.
Okay, so it's almost now 4 o'clock Central European time, and we have to close down the webinar. I would like to say thanks to Oscar and Johan, of course, but a very warm thanks to all of you attendees that took your time to listen in on this webinar. So you will receive the email most likely tomorrow morning, and there you can find information, so you can get in contact with Imagimob, and you will get a copy of the presentation from today. And as Oscar just said, you can also find a white paper, a guide that's covering some of the things that we went through today during the webinar. So thank you everyone that attended, and we will close down the webinar now. Thanks.
Thank you very much.